Weitao, Lu Xu, and Uri Heinz for asking me to chair this session. It's a great pleasure for me to introduce today's speaker, Dmytro Oliinychenko. And I was given a CV of his from Weitao. It's pretty impressive. I think, and let me describe a little bit about him. He got his BS degree and a master degree in physics and mathematics from Frankfurt Institute for Advanced Studies with Hannah Peterson. That time, that's Hannah's name. And now, then he got a PhD from Frankfurt. And now he has a postdoc at the Lawrence Berkeley National Lab. Already in very short scientific career, he already published 52 referred papers. That's very impressive. And also he got a very nice award. That's called Klaus Geiger Award. Most of us remember Klaus Geiger because his best presentations at the Hot Quarks 2018. And another thing I found very interesting, Dima somehow involved a lot in the physics Olympiad competitions. Not only himself as the winner of the 2006 Olympia winners, he also supervised many national teams, both in Germany and also in the United States. So he not only did a great contribution to physics, but also in helping young people get into physics. So with that introduction, I would like to ask Dima to present his seminar on review of the light nuclei production in both theoretical and experimental sites.
Thank you very much.
Please go ahead.
Thank you for the introduction, and thank you to all the organizers for inviting me to talk here. I'm going to talk about the light nuclei production, and as it is Rick Dimenez's seminar, it's kind of obvious that light nuclei production in heavy ion collisions. So let me go and introduce the main heroes of my story. This is deuteron, triton, helium-3, hypertriton, and they are antiparticles, and I will be also mentioning helium-4. They are all bound states of protons and neutrons, and in case of hypertriton, it's proton, neutron, and lambda, bound mostly by few MeV per particle, per nucleon, or per lambda. And the main question in general of all this research is the following. You have two light nuclei, you have two heavy ions, or maybe you have two protons, or proton-antiproton, or even electron-positron colliding at very high energy. And the question is how many light nuclei and antinuclei of each sort you are going to produce in this collision, and where do they fly and with which momentum. And if this, for some people, it's already an interesting question, but if you don't understand why we should study this kind of question, I have three motivations for you. And I'm going to unroll three motivations slowly and talk about the story behind each of them. Let's go to the first motivation. This is the International Space Station, flying 400 kilometers above your head. And it has a lot of scientific instruments on board. One of these instruments is called alpha magnetic spectrometer. Essentially, it's a particle detector in space. And it's very interesting. It's measuring particle fluxes that fly through it. It has magnetic field inside of it. So it can distinguish different particles. It can distinguish nuclei. It has measured a lot of different nuclei from carbon, boron, oxygen. This is a completely separate topic. It has measured protons and antiprotons. It has measured electrons and positrons. But so far, at least for published results, it hasn't measured any kind of light antinuclei and any antinuclei. It has not measured antideutrons. But there were some hints of antihelium, and this made people very excited already. But let me first say what kind of antihelium measurement it is. It is not published. It was presented in the conference several times. By now, it's roughly one event per year, and AMS is already there for, I think, 9 years. So what people say at the conferences is 6 events of anti-helium-3 and 2 events of anti-helium-4, maybe. So it is not published. It is not very clear if they are real events. But if they are real, it will be very, very exciting, because people start arguing where these events come from. And one possibility is completely ordinary. Some proton-proton in space collided at high energy and produced antinuclei, and these antinuclei are flying through the galaxy and finally getting into this alpha magnetic spectrometer. Or there is an exotic explanation. It's not a proton-proton collision. Maybe it's some antimatter clouds. Maybe it's some antimatter floating in the universe forever. Maybe there are some antimatter clouds, antimatter stars, or maybe there are some dark matter annihilations that we are seeing. How to distinguish? Well, we have to calculate the background. So there were some calculations of proton-proton to antihelium. It's really hard to calculate from first principles. I think nobody is even attempting to do that. People are using models. And one of these models, very popular one, is called coalescence model. So let's see what people calculated. 2017, Fear-Bloom and collaborators are calculating antihelium production and proton-proton, and they conclude that if those events are indeed measured, then it would be compatible with proton-proton colliding in the galaxy. Then publication in 2019, somewhat later publication, also calculate antihelium production from proton-proton. They are also using coalescence model. It's a different kind of coalescence model. There is a bunch of coalescence models. And their conclusion is proton-protons by almost 2 orders of magnitude, by 20 times, just cannot produce that much antihelium. If we are indeed seeing what AMS is seeing, then it should be something exotic. This is their conclusion. And then they write about anti-stars, then they reject possibility of anti-stars, and advocate presence of some anti-clouds in our galaxy, which will be very exciting. It will be groundbreaking discovery if it is true. Then it's not a very settling situation when there are completely opposite conclusions. There is a modern calculation, or completely modern. It is not yet published. It is on the archive, but I find it far more detailed than the previous calculations. It's a longer paper, and the calculation is, I would say, slightly more trustworthy, and still using coalescence model, but a different type of coalescence model. They're even called revisiting cosmic ray antinuclear fluxes with a new coalescence model. And they say again that antihelium production is probably compatible with proton-proton. All these coalescence models are phenomenological models. They are using some parameters, and these parameters are tuned to the data. What kind of data do we have? We have electron-positron collisions with antihelium production at 90 GeV from Aleph and Opal. We have antihelium production at 53 GeV from CERN, and we have ELISE data. And these models are calibrating to all of this data or to subsets of this data. So why do they give so different results? Because these coalescence models are very different. So just to understand what coalescence models are and why they are so different, let's have a short excursion over the coalescence models. What these coalescence models are. The coalescence models are saying the following thing. Coalescence models are saying nuclei are formed at the late stage of collision from protons and neutrons. So whatever happened, fireball, quark-gluon plasma, complicated interactions, light nuclei are formed from protons and neutrons in the very end. Then in the coalescence model, protons and neutrons would bind into nuclei if they're close in the phase space. So they are flying together and then they bind. This is what the coalescence models are saying, and mathematically this is expressed as distribution function of the nuclei is proportional to the distribution function of the proton to the power of number of protons, and distribution function of the neutrons to the power of number of neutrons, and momenta are taken so that they are flying together like this. So in their rest frame, what flies close binds together, you know. And there is a very important coefficient, this BA. This will be this proportionality coefficient. And A means the number of nucleons. So for deuteron, when they have 2 nucleons, it will be called B2. For triton, it will be called B3. For helium-4, it will be called B4. And for hypertriton, it's going to be B3 lambda. this is all called by the term BA. And in the very early coalescence models, it was just assumed to be constant. Let's take it just as constant and fit it from the data. And here is some early publication, very popular one from the 70s. And it used coalescence model where there was this P0 parameter. You can see that this is some volume in the momentum space. So this BA would be proportional to some volume in momentum space to power A-1. And on the left, you can see a picture how this model is describing data at relatively low energies. And to describe the data, they had to take different P0 for each of the nuclei. So it's not a universal constant, it had to be different for each nucleus. But look, this is a decent description of the data, especially for such a simple model. Now I would like to underline, this is not the state-of-art approach for BA. Many new things were discovered since the 70s. And one of the things, the first is that one can calculate this BA starting from the wave functions. I'm not going to go through all the formalism, but basically it's overlap of the wave function of the nucleus with the source, with the space of the source. So instead of having this volume in the phase space, you are going to have this integral which integrates over space, some kind of fireball, hotspots, whatever. There is this source function, which is just basically a correlator in space for protons and neutrons. This is this next line. And there is the neutron wave function. So this integral is basically overlap of wave function of neutron with the distribution of protons and neutrons in the source. And in this way, you can calculate this P0. It's going to be different for different nuclei because different nuclei have different wave functions. This was one progress, that you can use wave functions of the nuclei and actually calculate without making this a free parameter. And then later progress was that one can relate light nuclei production to femtoscopic correlations, because this is the formula for correlations. This is again integral of some wave function and again the same source function, the same correlations in space. And in femtoscopic correlation, the source function is just two flying protons, but it has to be antisymmetrized. And now you can see that this expression on the top and this expression on the bottom for the femtoscopic correlation, they are very similar expressions. They have integral over space, they have the source function, and they just have different wave function here. I think I might have forgotten to take the absolute value and square it here on the bottom. Maybe not. No, it's actually fine. So there is a relation between femtoscopic measurements and light nuclei production. This was a very important thing to be noticed. Out of this, one can actually derive formulas for the coefficient BA that we were mentioning, and this is going to be basically state of art now. If you assume that the source is homogeneous on the scale of the wave function size, if you assume that it is a Gaussian source, then you make some very reasonable approximation about difference of momentum. And you also assume that a many particle correlation function splits into two particle correlation. Then you can proceed to analytical derivation. It was done by Scheibel and Heinz. And very recently it was re-derived by Bloom and Takimoto. And you get this type of formula. I will go through the formula right now, but I will mention that these two calculations, the 1999 and the very recent one, they have a little discrepancy, which I think to date is not completely resolved. So it's still state of art, it's still ongoing calculations and debate. Let's look at the formula. So BA is, well, proportional to nucleus degeneracy. Most importantly, it's going to be inverse proportional to some volume. This is going to be some volume to power A-1. And this R perpendicular is size of the source in transverse direction. This R parallel is size of the source of the longitudinal direction. So you see, if the source is large, you can neglect all this. This is size of the nucleus. So you can neglect this one, and you will have dA inverse proportional to volume to power a minus 1. This is a very simple qualitative expectation from this calculation. Then it means that for deuteron, if you take a equals 2, then it will be 1 over volume. For triton, it will be 1 over volume squared. Then let's say if your source is relatively small, then you probably throw away this, or you set it to some constant, and your expectation is then that this BA is going to be constant in proton-proton. And if by this moment you already forgot what BA is, it's basically deuteron spectrum divided by square of the proton spectrum. It's how many deuterons you produce per pair of protons at necessary momentum.
I should just quickly interject here. The M versus MT discrepancy has been resolved. We realized that we were referring to radii in two different reference frames, which are related by a factor M over MT for the transverse radii.
Okay, thank you very much. That's nice to hear. Then one more simple qualitative prediction from this is that if you have larger charge multiplicity, so if you have more central collisions, you probably have the larger fireball size. If you have larger fireball size, you have smaller BA. Now let's check experimentally if these expectations are fulfilled. So this was naive, simple overview of coalescence models. Now let's check if the coalescence model is working well. First of all, coalescence model it is predicting the growth of B2 with the decrease of the volume. Let's look at the dependence on the transverse momentum. So we can see this is star measurement, but there are very similar measurements also from NA49. There are measurements from Elise, and they all are saying B2 is growing with MT, like here. And HBT volume is always decreasing with MT. I'm showing some data from star. There are also measurements from NA49. There are measurements from Elise. This is pretty universal that when you look at higher momentum, the system size looks smaller, the fireball size looks smaller. And indeed, it is compatible with coalescence expectations. I'm not checking quantitatively now, but qualitatively, it agrees very well. Let's go further. Let's check at the dependence of transverse momentum for, this was dependent on transverse momentum. So this is now Elise data. And you can see that I was saying in proton-proton, you're going to have B2 constant, and already in peripheral, you have it almost constant. In proton-proton, it's indeed constant. So here it works as well. And for helium, it also works. And for helium, you can see that B3 is growing a bit faster, which is also reasonable because you would have 1 over volume squared. So you expect it to grow faster. Still compatible with coalescence expectation. Very nice. Then next thing, you go from very central events with large multiplicity, so it will be large volume in terms of coalescence, and this will be smaller volume. And smaller volume is the largest B2. Oh, exactly as coalescence would expect. And now you look at the dependence of B2 at particular momentum against collision energy. And you can see that in B2, star is measuring some kind of minimum. In HBT volume, you also have some minimum, but it's completely different energy. This minimum of HBT is at 6 GeV. Here you don't see any minimum. But what you see is here HBT volume is actually growing. So it's not really so much compatible. But then if you look at the larger scale and you just plot BA for different experiments, and there is no star here, or less star points in this plot, and plot 1 over volume of HBT, and for helium, for triton, you plot 1 over volume HBT squared, and on this scale, it looks pretty much compatible. So it's not completely clear to me. It has to be verified more precisely, let's say. Now, I was showing only qualitative just for you to understand and appreciate, but there is also more quantitative comparison, very recent, by Bloom and Takimoto, and their recent continuation, it's not yet published on the archive. And they are trying to make this comparison more quantitative and putting on the x-axis the HBT radii and B2 on the y-axis, and this band is theoretical prediction, this is experimental measurement, and you can see that they are in the wide agreement, like agreement within the error bars. But when I look at this picture, one thing is not very satisfying to me. The error bars are huge both in theory and experiment. Why they are so big in experiment? In experiment, they are big because of the HBT radii measurement, because those measurements have some error bars. Also, look at this plots. It's a very big error bar also in theory, because, and this error bar is coming because they are substituting HBT radii, and there is also HBT lambda parameter, and those have experimentally large errors. So here I would like to stop, and I would like to announce a little challenge. Like when I'm looking at these plots, it's not very satisfying because of these huge error bars. The question is, should experiments measure better? And I think it would be rather hard for experiments to improve much on precision. I think here theory has to do a little bit better. There should be some simple phenomenological formula with all these dependencies qualitatively reproducible so nicely. One can just take some simple parameterization of HBT radii over different energies, over different centralities, over different PT, and make some simple phenomenological formula to fit this BA at different energies, at different multiplicities, and then this theoretical error bar shouldn't be so high. I think one can do better here, and I would be happy if you comment on that, or if you do this work. So this is the current status. It's coalescence model seems to be working, seems to be describing the data, but the error bars are huge, and there are a lot of points of improvement, and active work ongoing. Now it is clear that coalescence model is making an interesting prediction. It is saying that if the wave function of the produced nucleus is large in space, if it spans for more than the fireball size, and this is going to suppress the production, then we have something that is really large. The hypertriton H3 lambda is basically a deuteron bound to lambda, and this lambda is kind of flying around deuteron. It's bound by just 130 keV around it, and the size is around 10 Fermi. So it's quite a big object on this scale of the fireball, even in heavy ion collisions. And it is a good object to test coalescence model. It was realized just recently, and one big contribution to this is this paper by Bellini and Calvite. However, Bellini and Calvite took a rather simplified wave function of this lambda in their calculation, and there are now more calculations where a more complicated wave function is taken. It's still Gaussian, but at least it is Gaussian different in different directions, with different radii in different directions. And it seems now that coalescence model is roughly compatible with the data. But again, if you look at the plots, this is one of the plots from Bellini, Bloom, Calvite, and Puccio. And you can see it's a rough agreement. This theoretical error bar is quite large. It's an agreement, but it has to be studied further, and this error bar has to be decreased. So on the one hand, we are waiting for experimental measurements that would measure more hypertriton, and we are waiting for theoretical calculation with some better precision. This was the hypertriton story. Now, I would like to add that I was presenting now analytical calculations of coalescence, and they are all using the Gaussian source approximation. And in principle, one doesn't have to stick to Gaussian source. One can have more realistic sources, and that is achieved by running some dynamical code. It can be hydro plus transport, or just transport. And then in the end, with the nucleons that you have, they have more realistic spatial distribution. Then you can perform a coalescence. But now let's look how it's happening. This is one of the publications I like. The transport code there is URQMD, but there are also works with GEM. I'm going to present them later. There are different works with transport codes, and the recipe to make a deuteron is the following: just take a nucleon pair, roll them back to the last of the interaction times, to the latest of the interaction times, basically to kinetic freeze-out, then boost them to the rest frame. And then if in their rest frame they are close enough, and close enough is 2 free parameters, then just bind them together. And then there is some additional procedure happening with isospin factors. And with this very simple procedure, they are able to describe the data deuteron yields as a function of energy and deuteron yield as a function of centrality pretty well. And I'm just showing 2 plots. There are more there. However, with this type of coalescence, there are often free parameters, and these free parameters seem to be very different in different models. And every type of transport and hydrodynamics is doing this kind of procedure by their own algorithm. And so far, there is no established algorithm. So on the one hand, we have a good description. We have a realistic source. On the other hand, there is some arbitrarity entering through this algorithm. And I think there is some work on theoretical side to create a prescription that everybody would adopt. Because nowadays, everybody is doing their own way. And this was just deuteron. It's more complicated for triton, helium-3, H3 lambda. There, people become even more creative with the coalescence because there are more ways to do it. With this, I have finished the first motivation. If you remember, the first motivation was production of anti-nuclei in space. And I think that for fulfilling the first motivation, one can just, so if we are able, with any phenomenological model, with any parameters, with anything, if we are just able to predict production of flight nuclei precisely, then we win. We are happy because then we can calculate the background for the anti-nuclei in space. And maybe, if the nature is kind, as they write in one of the papers, then maybe we can discover antimatter in the universe. Now, the second motivation is closer to us heavy ion people. This is the phase diagram of the strongly interacting matter. If you go to high temperature or high density, which is represented here by barochemical potential, and you get quark-gluon plasma. And we know that there is a transition, that there is a crossover quark-gluon plasma at low baryon density, so when you have equal amount of baryons and antibaryons. But at high baryon density, when you have more baryons than antibaryons, we are not sure if there is a phase transition here or if it is a crossover. But if there is a phase transition, there should be a critical point. So Dmytro Oliinychenko experiment is largely dedicated to the search of this critical point. And one particular feature of critical point that is very universal is that spatial fluctuations around the critical point tend to increase. The problem is that this is spatial fluctuations, and we are measuring momentum space. But luckily, there was an interesting idea proposed by Kaiji Asun and Cheminko and others. And this is to probe spatial fluctuation through the light nuclei production. This is, again, a type of simple coalescence model. You have neutron density and proton density, and they can fluctuate, this is delta density, around some average. And then you calculate the amount of deuterons. You integrate out momentum part. You don't care about momentum part so far. But in the coordinate part, you get integral of proton times neutron, because deuteron is proton and neutron. So you get a product of proton and neutron density. And then you substitute this average plus fluctuations, and you get this expression where C and P is measuring correlations between protons and neutrons. Then you do the same for triton. Triton is proton and neutron, so you have proton density times neutron density times neutron. Also substitute these fluctuations, and then you get an expression where you have correlations of protons and neutrons and fluctuation of neutron density. Now, if you build a smart ratio, lots of things cancel. This ratio is triton times proton over deuteron squared, and you are canceling temperature, you are canceling chemical potentials, you are canceling basically everything except the fluctuations. So this ratio is going to be a measure of fluctuations. This 1/2 square root of 3 is a thermal ratio, so the thermal model will also predict this kind of ratio. And this is completely dependent on fluctuations and correlations. So essentially, this coalescence model is saying, if you measure light nuclei, they are sensitive to spatial density fluctuations, and you will see something special around the critical point. And without fluctuations, it's predicting the following. It's predicting that this ratio is going to be independent on almost anything. It's going to be independent on the energy. It's going to be independent on the centrality. It's going to be independent on the collision system, or at least this is what this model is predicting. So this is this prediction shown on the plot. The ratio is on the y-axis, the energy, the collision energy is on the x-axis. This is coalescence prediction. There is also some different prediction. There is a thermal model that says that light nuclei are formed early, and this is the thermal model prediction. And funny enough, the thermal model prediction is basically the coalescence model prediction times the factor that comes from resonance decays. And you get this difference because in coalescence, light nuclei are formed at the late stage of the collision. And in thermal model, light nuclei are formed at the earliest stage of collision where resonances have not decayed yet to proton. So it's essentially you get the same proton formation, light nuclei formation from the proton, but then additional factor of resonances decaying into protons, and then you get this factor to protons. So you get this difference because at high energies, 2/3 of the protons are coming from resonance decays. Then there is a more advanced calculation in the transport approach, where you run transport approach and do the coalescence. And interestingly, it agrees with simple analytical expectation. It is non-trivial because in transport you have some spatial fluctuations, you have some interactions, you have collisions. So it is non-trivial that you are going to also get this flattish behavior from transport plus coalescence, but you get it. The height of this line can be going up and down. It depends on the parameters of this coalescence, but the fact that it is flat is non-trivial. And the data, let's look at the data. Here are the data. These are Na49 measurements from CERN. Stars are star measurement from STAR, from RIG. And these are ELISE measurements. And then you can see that this ratio is behaving in a very interesting way. You would expect that at critical point fluctuations grow, and this ratio would make some bump around the critical point, and in experiment you see this bump. So everybody should be very excited, I think, about this. You are seeing this huge bump. Are we observing a critical point? And the answer is nobody knows, because there is no model with a critical point that would explain this bump. And even background models like coalescence and thermal don't really agree very much on what the background without critical point should be. And also there is some tension between the star highest point and the least points, because both coalescence and thermal model would say that at high energies, and you don't expect critical point there, high energies, this ratio should be saturating. And well, it is not really looking like it's saturating. So this is very exciting, and this is huge motivation to go forward and understand light nuclei better. And it was also motivation for me to study light nuclei. There is some modern development on that. People tried to understand where this bump could be coming from, and how critical point could influence light nuclei production. And one idea is coming from Edward Shurak and Juan Torres Rincon. In there are several publications, I'm citing only one. And they suggest that around the critical point, nucleon-nucleon interaction becomes really very attractive. Then this ratio is proportional to a factor which depends on this potential. and then you get a bump around the critical point. And then they are also suggesting that there are ratios that are more sensitive to the same thing, because here you have the same thing to power 3. And if you construct this ratio, which involves helium-4, so you have to measure helium-4, it will be even more sensitive to the critical point. Then they also make an interesting point that helium-4 excited states might play a role because, well, this attractive potential is now going to bind helium-4 very strongly. So it is interesting also to see how helium-4 exciting states are behaving. And there is a recent work of Vovchenko, Donigus, Cardan, Lawrence, and Horst Stoker, and they are looking at helium-4 excited states just in the thermal model without these potentials. And you can see that at lower energy, yeah, there is some influence. It's not making you a bump, but you have to take this helium-4 excited states into account. This is interesting, modern recent development. So now I have already mentioned thermal model. Let's look what the thermal model is. Especially with the LHC data, it was quite recently suggested that you can fit the light nuclei yields in the same way that you fit all the hadron yields with the thermal model. The thermal model for the light nuclei, because they don't have decays into them, is this simple formula. If you look at it, it is essentially a Maxwell formula for the amount of thermal nuclei at temperature T. And the temperature T that fits the light nuclei is the same temperature that fits the hadron yields. So based on this simple model, people conjecture that maybe light nuclei are formed at the same time when all the hadrons are formed. And at LHC, this will be temperature of around 155 MeV. However, if you look at the nuclei momentum spectra, they correspond to kinetic temperature of around 110 MeV. So in the thermal model, you get a question, how do these nuclei survive between 155 MeV and 110 MeV? And all these nuclei are bound by just few MeV. So the whole situation is called snowballs in hell. And hell would be this temperature of fireball. Now officially the temperature of hell is 155 MeV. And snowballs are going to be this nuclei. So snowballs in hell. And this is the third motivation to study the light nuclei, is to understand the snowballs in hell puzzle. So there is this question about what happens to the light nuclei at this very high temperature. Are they getting destroyed, or how they survive? At this point, I have introduced two models. There is blast wave model, and there is a thermal model. There is thermal model and there is coalescence model. And there are some debates going on about the differences between these two models. And because these debates are sometimes very weird, I would like to point one particular difference and similarity between blast wave calculation and coalescence calculation. A thermal model by itself is just predicting particle yields. So you need something to get momentum spectra, and for momentum spectra, usually blast wave model is used. And blast wave model is essentially a Cooper-Frey formula applied on some kind of hypersurface, and this d sigma mu will be elements of this hypersurface. And you can write the blast wave expression like this, and then if you take a concrete hypersurface and integrate it, then you get the usual Siemens-Rasmussen formula. And coalescence model is not very much different. The coalescence model is different only by this little factor, which is a kind of homogeneity factor. This factor is measuring how homogeneous is fireball on the size of the wave function, or on the scale of the wave function. And if the fireball is big and homogeneous, then coalescence model and blast wave model are going to give exactly the same result. Why do thermal model prediction and coalescence model prediction is different? it's mainly because of the resonance decays, because the chemical potentials of protons here and chemical potential of protons here are different. In the blast wave model, they are before resonance decays, and in coalescence model, they are after resonance decays. So the difference between the models is not as huge as people might think. And coming back to the thermal model, yeah, the question is, and the puzzle is, how the nuclei survive this high temperature. And there is even this funny cartoon, this artistic representation. There is very hot quark gluon plasma and some neutron barely escaping this hell of quark gluon plasma. So to study this, now I'm going to finally talk about something that I did. We have created a model with Longang Pang and Hanna, now Elfner, and Volker. We have created a model that resembles both thermal model and coalescence in a way. We are taking a dynamical approach, hydrodynamics at early stage and hadronic transport kinetic theory at later stage, and we are doing particularization transition from one to another exactly at 155 MeV. And the sampling of particle is thermal. So essentially we are getting thermal nuclei, thermal neutrons in this case, at 155. These neutrons interact with the known cross sections, and then we see what emerges in the end. So the neutron here is implemented explicitly as a point-like particle, but some people are confusing. I'm saying point-like particle, but when it's interacting, the cross section is finite. And the role of the size of the neutron is played by the cross section here. And it is allowed to interact in the hadronic afterburner. It is very interesting to look at the cross sections. In this puzzle of snowballs in hell, you assume that every neutron with binding energy of 2 MeV hit by some pion with 100 MeV is going to be destroyed. But it is not true. The elastic cross section is reaching 70 millibarn here. This is the elastic cross section with the pink line. So not every pion that hits neutron is going to break it. Actually, in one quarter of cases, pions hitting neutron are just not going to do anything with it. It's elastic reaction. But then the cross section of inelastic reaction is also quite large. It's around 160 millibarn here. But where there is a reaction with a large cross section, there is going to be an inverse reaction. So we implement the reaction of neutrons with pions and nucleons, and we implement this detailed balance. So we implement the reverse reactions, and we implement the detailed balance principle. So the rates of the reverse reaction is connected to the cross section of the forward reaction, which we know. And we test this in a box that this detailed cross section is fulfilled with large precision. And then we are able to describe the neutron spectra at LHC. Now I'm reminding this B2 is ratio of neutron spectra over proton spectrum squared. And also describing B2 at high centrality, which some people say this is not going to work for smaller system, but it's working for small system. It's working for larger centrality, and it's no free parameters. And it's describing data pretty well. So they're also describing neutron V2. Then one can ask a question where neutrons are really originating from. So what happens to neutrons in these simulations? Are they just formed at the end of the hydrodynamics and then fly away? Or they have a lot of collisions in the transport simulation? And it turns out that very little fraction of neutrons that end up in the detector actually originate from the hydrodynamics. Most of them are, most of the produced neutrons are coming from the last collision. So it's roughly as coalescence would say. So what we're doing here is resembling both thermal model and coalescence in a way. And one can look at the reaction that produces these neutrons. And main reaction is reaction with pion catalysis that catalyzes neutron production from proton and neutron. And you can see that this reaction is going in forward and reverse direction with roughly equal rates. So it is kind of equilibrated. Then if you look at how neutron multiplicity in this simulation is changing with time, it is almost constant. Then we asked ourselves a question, what if we don't sample neutrons at the hydrodynamics at all? what if we start with no deuterons, and then all the deuterons are formed in the hadronic afterburner, then we get this blue line, which is somewhat less, but we are still close to the data. It's in rough agreement with the data still, which is the data are shown with this purple arrow. So it is even a scenario is possible where no deuterons are formed at all at particularization and all deuterons come from the afterburner, but it's more consistent with the data if you actually sample deuterons. And just for fun, we tried what happens if we sample too many deuterons and then it goes down. And it doesn't go down as far as we want to describe the data, just because the system freezes out. Because this there are not enough collisions in the fireball to sustain these reactions further going down. So I would say there is quite a solution to the snowballs in hell puzzle, and the solution is the following: there are stable hadron yields like pions, nucleons that are already fixed at the chemical freeze out if you count them with the resonances that are going to decay into them, and nuclei are kept in partial, or some people call it relative equilibrium, by large cross sections of this catalysis reaction. Some kind of hadron breaks up nucleus into nucleon and also creates nucleons out of nucleons. And I have shown this for deuterons, but there are also other works where people have shown that it works for other measured nuclei. And you can see that it works to some extent even if no nuclei are produced at the chemical freeze out. And one can also go, it was LHC energy, one can also go to lower energy. And now I'm taking a different hydro code. This is now with music because it can be applied at lower energy. And it's still describing the data at lower energy for deuterons down to 7.7 GeV, and with the same mechanism, exactly the same reactions, it didn't change anything in the code. And describing deuteron yields and describing deuteron mean PT. So basically describing the data with exactly the same mechanism down to 7 GeV. So now I would like to go into conclusion. This is the first conclusion. We have three motivations to go for better understanding of light nuclei production. What do we get if we understand light nuclei production better? If we do, then we can precisely estimate the background for antimatter in space from proton-proton, from proton-helium, from helium-helium collisions. And maybe if we are lucky, then we discover antimatter clouds in the universe, and this will be a huge discovery. Then if we understand the light nuclei production, we might be using it for detecting the critical point from density fluctuations from this ratio that was proposed first, or there are other ratios that might be more sensitive. However, on this way, for potential benefits, there are also challenges, and you can see there are more challenges than benefits. It would be really nice to get some model that would just, maybe with few parameters, but we'll just get all the experimental dependencies that we are measuring. So some phenomenology is welcome here. And apparently the phenomenology should be based on some coalescence parameterization, but it doesn't necessarily need to be. Then we need to improve existing models. And there is now quite a strong push for testing coalescence, for improving it. Then we need more models, including critical points. So far, we have only these works of Edward Shuriak and Juan Torres Rincon. We need something more to include critical point and understand light nuclei production in a model with a critical point. It seems to be still an open question if the wave function size matters. It is the most stringent test is in small system with a hypertriton, and it is ongoing. We need more measurements of hypertriton, and we need more precise calculations. And you have seen those error bars. We need to decrease error bars both on experiment and theoretical calculation. And for transport approaches and for dynamical approaches, it will be useful to know the exclusive cross sections of nuclei with hadrons, especially the inelastic cross section, which the data are very scarce. So it will be nice if these cross sections are measured or if they are analytically computed. And with this, I would like to thank you for your attention and welcome your questions.